So I will talk about what we call Fenics-HPC. So Fenics, it's a large project we started in 2003. Now it has grown to a very large project, maybe estimate 30 developers, something like 50,000 downloads per year. So it's an open source umbrella software project for automated solution of partial differential equations, and I will explain what this means. And Fenics stands for finite elements systematized with computer science. So traditionally, a lot of finite element software was written maybe by a mathematical community, but here we try to use computer science to make everything automatic and so on. And our branch then is the high performance computing branch. And we developed this mainly at KTH in Sweden and Beckham in the Basque country. And just to introduce my colleagues, so Jem is here, Massimiliano is here, Niklas Jansson is at KTH, so he has been responsible mostly for most of the HPC research and software development. And Johan Hoffman you met yesterday. And what we try to do is to do automated, adaptive, high-performance finite element computing, and then the main applications are in turbulent flow and fluid structure interaction. And here you can see some typical images. So aerodynamics, and here is ocean energy, marine energy, and here is the application of a floating wind turbine. So here is a sort of a bird's eye overview of what is Fenics, what is this automation. So the idea is that we input a partial differential equation. Here is the residual, so an equation in mathematical notation, and we write the mathematical notation then in ASCII text. So this is a high-level description, and this is actually a Python, so it's a very high level. And then this is then compiled to a low-level source code that can be hundreds of thousands of lines long to generate code to construct the linear system. That we call automated discretization. Another aspect is automated error control. So in scientific computing, to solve a partial differential equation numerically, you introduce a mesh in the finite element setting. This corresponds to a function space, but this is related to the mesh is related to the error, how far away you are from an exact solution, and typically this is constructed manually. So here we by general error estimates we can construct this automatically to satisfy tolerance on the error. Here M stands for an output quantity. For example, the drag force on an aircraft could be the quantity you're interested in. And then we have an error estimate that generates an adaptive method to optimize the error in this quantity. So I will show examples of this. So we give a starting guess for the mesh, and then iteratively an optimal mesh is constructed then to satisfy this. So that is automated error control, the second aspect. A third aspect can be said to be automated modeling. So we do compute turbulent flow. And the standard approach to turbulence is that you introduce a parametrized model where you introduce a viscous term with parameters that have to be tuned to benchmarks and so on. Here the approach is that we don't have any explicit parameters. We don't have any turbulence models. So with a numerical stabilization as part of the method, we identify this as modeling the subscales automatically. So I will also show examples of this. And then another aspect can be automated optimization. This is a large activity in the Fenics project. So our part of this has mostly been the adaptive error control, but there are a lot of other aspects of optimization that a lot of other people are active in. So you can say the goal is to automatically generate the solution, the mesh, and the program given the PDE then. So what is the challenge we're trying to solve? So we're trying to solve aerodynamics, for example, for an aircraft. The model is clear. It's the incompressible Navier-Stokes equations. But this is very challenging to solve. So we can identify a Reynolds number, which is the ratio between the convective and viscous forces. And for an aircraft, the Reynolds number is very high. So turbulent flow can be described as a multitude of scales. And the smallest scale looks like this. And one approach is to try to resolve all of these scales. But then the cost scales like this. And for an aircraft, for example, the Reynolds number is about 10 to the 8. So that means we need about 10 to the 18 mesh points to resolve all of these scales. So this is impossible even on the largest supercomputer today. So we cannot, sort of with brute force, compute the aerodynamic forces on an aircraft. So we need cheaper methods. And our approach for a number of years, so this work was started by Claes Jansson and Johan Hoffman. I joined a few years ago, and now we're a large team developing this approach. So it's a space-time finite element method with a Galerkin least square stabilization. So we can identify that the finite element method is, we take the residual, this equation, should be orthogonal to a test space or to test functions. And the stabilization takes this form. So it's a square term of the residual. So it's a simple structure. And this can be shown to give a stability, a mathematical stability estimate. And then we have adaptive error control. This means again that we can formulate the relation between the error and this residual, where we introduce an adjoint solution, a sensitivity function. We solve an adjoint problem. And then we have an expression for the error. And then we can evaluate this, the residual, where we plug in this adjoint solution. And this gives information where we need to refine the mesh. We have the most expensive part, you could say, of this turbulent flow. If you look at the aircraft here, is a very sharp boundary layer. So we have a high gradient at the boundary where the flow goes from 0 velocity to high velocity. So what we propose is a slip boundary condition. So we model this condition as 0 friction. And this gives a huge cost saving, as we will see. Yes. And then, as I said, we don't have any turbulence model, so the dissipation comes from this stabilization. In Fenics, this is an example of the notation. So here we put these Navier-Stokes equations. In Fenics, it looks like this. So you can see that we have, for example, the gradient of the pressure. We write it like this. It's a very compact form. And this is an example of the generated code. So this is something we don't want to write manually. We want to just write the equation, the low-level loops of numerical integration and so on. That can be done automatically. This is something we never have to do. And this is the structure. I will skip this. So we have different components in Fenics. As I said, mainly the work of Niklas Jansson, our colleague who is an expert in parallel computing. We have been able to show optimal scaling to about 20,000 cores, so we can efficiently use supercomputers. The main application I will show now in this presentation is a benchmark for an aircraft. So NASA and Boeing organize a high lift prediction workshop. So they give detailed experiments of an aircraft in a wind tunnel. And teams from around the world are invited to try to predict sort of the experiment. So we have participated with good results, and we were the only team of about 30 2 years ago to use an adaptive methodology. So this is something that the organizers, the NASA organizers, thought was interesting and important for the field. So our adaptive methodology was highlighted in the summary, and we could capture pre-stall results well. Here it's a detailed plot, but just on the x-axis is the angle of attack. So the aircraft sort of increases angle, and here is the lift force. So as the angle of attack is increased, the more you have more and more lift, eventually you get stall. So then you lose the lift, and we can capture then this before the stall. We capture the aerodynamic forces to within about 1.5% of the experiment. And some of the other submitted results then, using, for example, the standard software like Fluent and Exa PowerFlow, they're about 10% off. So this, and we can also do this with about an order of magnitude cheaper simulation, mainly due to this adaptivity and this slip boundary condition. So this seems very promising for predicting turbulent flow. So now we have to hurry up. These are some of the quantities. So this is the residual. It is sort of how well we can locally satisfy the equation. It's large in the turbulent wake. And this is this sensitivity function, the adjoint. So this, you could say, transports. We want to predict the force on the surface. So this becomes a source, and this is transported upstream. So it's like solving the equations backwards. And this is the starting mesh here. And after 5 adaptive iterations, this is sort of the optimal mesh that gives this 1.5% error. Then we can extend the methodology to fluid structure interaction. I will skip this now. So what are we doing in MSO4SC? So we can do challenging applications with societal relevance in an automated way on supercomputers. Here we have 2 pilots, a floating wind turbine that I will come back to later, a 3D air quality prediction where we collaborate with the Soltans team. We are responsible for the CFD. So Massimiliano has started on that. We are also then adapting Fenics-HPC to the MSO4SC framework. So this means containers, interface to the orchestrator and the portal, benchmarking and testing. And Jem will present some recent results on that. So thank you very much. Now we switch.
Hello, everyone. Can you? Yes. My name is Degirmenci. I am a PhD student of Johan Jansson and Johan Hoffman, and soon to defend. And since 1 month, I have been working in Basque Center for Applied Mathematics. And I will talk first about the work package 3, and our work will be focused on these 2 layers. This image I have taken yesterday from Javier. I think he forgot Fenics-HPC in that 1 layer, but here there is some wind turbine that corresponds to maybe our future application. Here is the outline. I will talk a little bit about the supercomputers used. I will give the overview of a simple test. Then I will start describing the framework, which Johan has already done actually. I will present some unfair comparison results, give a more complicated test, continue presenting the framework, talk a little bit about our future work with MSO4SC, and I will lastly talk a little bit about vocal fault simulations for fluid structure interaction application. Okay, this is the BESCO supercomputer at KTH that we have been using. It was ranked 32 in 2014, but today in the morning I checked and it's number 74 in top 500 list. And it has a really fast interconnect, and we compiled on the operating system our codes for comparisons. And since 1 month almost I have access to Fenics supercomputer, which is a bit smaller, but here we can run the singularity images as well as on the operating system. And we also ported our framework to other supercomputers in the past, like it has been used on IBM Blue Gene, SGI Origin, and it's done with Auto Tools. And before I describe the finite element framework, I will do it with an example, with a simple one, Poisson equation. And with simple calculus knowledge, if you have a nice F, you can exactly find the solution, and it's good for verification of your code. And here you see the weak formulation of the same problem. And you search for solutions in the finite dimensional spaces, which is the Galerkin approximation. And the Fenics framework is a finite element framework with different components. Fiat is the finite element automated tabulator, and the second component is Fenics form compiler. So we provide a Python file which really represents, which is really similar to the weak form, and this form compiler creates, as Johan mentioned, really big header and C++ files that has the quadrature rules for computing the integrals and Jacobians and everything. And you just include this and generally don't look inside. Okay, and the Dolphin component is a collection of classes for parallel implementation of the matrices, the vectors, and the assembly, and also parallel mesh. For this Poisson example, I show some part of the code, and I also had some timings for different portions of the code. Okay, so I have set unfair performance comparison because I have run this example on BESCO, FT2, and on a singularity image that I have created on this computer. And I immediately know that I did something wrong because the singularity image was faster than the others. And I later saw that I forgot the optimization flag in these other guys, so that was unfair. But still, I think it shows that the singularity approach is promising because it's not it's head-to-head with the others, let's say. Okay, here is a bigger example, and you see a platform with has 4 legs, and flow is passing over this platform. And on top, it's the primal solution, and on the bottom, it's the dual solution to the dual problem, which will be used for adaptively refining the mesh. This mesh is very coarse, but it will be optimally refined with respect to the drag force on the platform. And after running this example, we immediately saw that the BESCO was up 3 or 4 times faster due to the interconnect, high-speed interconnect that it has. Okay, so Now I come to the last part of the framework, which is Unicorn. It's unified continuum models for fluid structure interaction, adaptive mesh refinement, turbulence modeling, contact modeling, moving mesh, mesh smoothing, and acoustic coupling algorithms. And what we want to achieve with MSO4SC, sorry for the ugly arrows, but we want to incorporate automated testing. So we already have done some testing tools for simple verifications in the past with Jenkins, but we also want to use these singularity images to do some tests on scaling, like weak scaling and strong scaling. And when you change something in some components, you can be sure that you are not destroying the scaling of the framework. Okay, and I will continue with the vocal folds simulation, which was my work during the main part of my work during the thesis. Here I show two geometries. The one in the top is a simplified geometry to create the vowel E, and there are these artificial vocal folds connected to a vocal tract to produce this E sound. And this work was done in the context of another EU project called Unison, where you see the web address. And this model was actually built by our partners. The vocal folds, artificial vocal folds, were made from silica by our partners in Erlangen University, and the vocal tract was 3D printed as well, and measurements were taken on that. And on the lower side you see a more realistic geometry where the vocal tract is extracted from MRI images by Speech, Music and Hearing department of KTH. And this vocal cartilage model is extracted from another open source, now they became open source, Artisynth software. Okay, here is our fluid structure interaction model. We solve the partial differential equations for conservation of momentum, mass, and constitutive laws for the stress. And I will show some videos for our results, if I can. So as I have said, we have a monolithic solver for fluid and structure, and here is some simulation where air flows and it makes the structures vibrate. And there is also the problem when they come too close, the contact phenomenon, which is also in the model, which is resolved in the model. And this simulation was done with around 500,000 vertices. I will show another video where you see the contact more closely. And also there is a jet forming between the vocal folds, which is quite difficult in terms of numerics, because we really have to resolve the problematic region, the region between the vocal folds, for oscillations to start. And on a more realistic geometry, we have these simulations again with 500,000 vertices. where you see the vocal tract on the rest of the flow, and the vibration of the vocal folds here. And this pattern of contact, I will come to that. It's some good validation that we have achieved. Here is a closer look at the contact pattern happening between the vocal folds in the realistic geometry. Okay. So what did we achieve? We were able to, maybe I should also show you this one. So this is this simulation. In the simulation, we also coupled fluid structure interaction simulation to the acoustic model that we have. It was a one-way model, but we got some good results anyway. So for the vowel E, we were able to capture the first three formants of the vowel, and this was a good result, not done before with a unified approach. And as I said, the glottal wave in the contact has also been captured. So this is a sketch which is quite. This sketch explains how the vocal folds contact, and we also could capture this with our simulations, with our contact models. And this was a strong validation on our for the model for our case. Okay, and here is some of the articles referring to these results. And thank you for your patience.